Good afternoon, everybody. My name is Boelo Schuur. I'm the Scientific Vice President of the European Federation of Chemical Engineering. I've recently joined the board of the EFCE, and it is an honor for me to serve the chemical engineering community in this role. As the Vice President, it is my task to support our scientific groups. That means that it's the working parties and the sections of the EFCE in their role to promote chemical engineering and to our fellow chemical engineers, but also to the wider society in Europe, but also over the whole world. We hope that everybody will benefit from all the good work that we chemical engineers do. Personally, I'm a chemical engineer from the north of the Netherlands. I grew up in Groningen. I got my PhD from the University of Groningen. And 12 years ago, I joined the University of Twente, where I'm currently a full professor in sustainable separation technology. Next to my academic position, I also hold a position as the program director at the Institute for Sustainable Process Technology, where I had the cluster of separations for circularity. And in that role, as well as in my role at the EFCE, I promote the collaboration between industry and academia. And it's my vision that it is essential that we do not work as academicians in a separate world from the industry, but that together with industry, we foster the best results and we develop a sustainable society. As such, I think the working parties have an excellent role and have a key opportunity to guide us towards next generation processes. Having said this, I'm thrilled to see that today we have a spotlight talk from our fluid separations working party, chaired by an industrial chair, Kooijman, with academics to speak about next generation distillation processes. And before zooming into the details of today, in general, the spotlight talks that we are a part of today is a series that has been initiated during the COVID pandemics in 2020. And as a result of the success of this series, the EFCE board has decided to continue this. And every year we will have a series of spotlight talks. And in the years that we don't have an in-person European Conference on Chemical Engineering, we even have two. So this year in the fall, we have another series. And next year, we will have the European Conference on Chemical Engineering again. So next to this spotlight talk, we have a couple more coming up next week. And you can find the links where you also found the link for this session. And you can subscribe and participate in those sessions as well. So the EFCE is representing chemical engineers in over 30 countries, and we represent over 100,000 chemical engineers. And these are at the core of the EFCE activities together in our working parties. I would like to close this introduction by thanking the speakers of today, in general also the participations to the spotlight talks, and of course also Martine Poe for organizing the spotlight series. I hope you will have a great spotlight talk series today on distillation, and I wish everybody a good afternoon, and I give the word to Kooijman, the chair of the Fluid Separation Working Party. Harry.
Thank you. Thank you, Boelo. Welcome to the spotlight on distillation, and I have the program that I wanted to share with today's speakers visible. We will be starting off with Professor Rakesh Agrawal, formerly with Air Products and now at Purdue University. We will talk about synthesis of energy-efficient distillation processes. That talk will be followed by Kai Kruber, who is filling in for Professor Mirko Skiborski from the Technical University of Hamburg, towards a systematic design of distillation-based separation processes. And we will round up with Eva Sorensen, at UCL, University College London, on the optimal design and operation of hybrid reactive distillation columns. But before we end up with a round discussion and conclusion, I would like to remind that all participants write their questions in the Q&A box and mute during the presentations, and then we will unmute during the question sessions. The talks are about 20 minutes long, 25 minutes maximum, and so that we have about at least 5 minutes for questions and answers, but preferably a little bit longer. Before we start, I would like to also show you the Working Party website. The Working Party of Fluid Separations has its own website. If I can find it, here it is. And you can find this at efce.info. And then you can move to scientific groups. And here, all the working parties are listed. You can see crystallization, drying, but also fluid separations. And you click the link, you will go to the working party's own website, where I would like to point out to you that you can look at the previous activity meetings. And in here you see all the previous meetings that the working party has, and you can also look up for some of the, or a lot of the talks. You can look up, for example, on direct air capture, a talk by Richard Darton in 2020. 2021, I think, or this one is 2019, excuse me. But you can find much more information there. And it will enable you to find much more about distillation than you may be aware of. We keep having meetings every year in between the DNA conferences, the distillation and absorption conferences. And everybody, these meetings are open to everybody, and not everybody is aware. And I hope to see some of you also at these meetings. Now, I think it is time that I hand over the word to Professor Agrawal of Purdue. Rakesh, please go ahead.
Okay, thank you, Harry. And so with that, let me just put it on show. Okay, hi everyone. So today what I will do is I will talk about the synthesis of multi-component distillation column sequences. And in collaboration with ExxonMobil, we worked on crude distillation. So I thought I will use that as an example to illustrate various steps. And so what I will do is I will walk you through the various steps. So the first of all, I will just tell you quickly what the crude oil distillation is and why it is challenging. And then I will take you through the methodology of creating all those possible configurations. And in the end, I will show you the results. Okay, so that's the plan. And why crude distillation is the 7th product distillation, as you can see from here. Let me just get a cursor here. So yeah, so it is a 7th product distillation. And so the question is it is a very mature technology. And distillation, since everyone is a distillation person here, I will not go through this slide why distillation is important. But just in a nutshell, distillation consumes quite a bit of energy. And in the United States, it consumes, by various estimations, roughly 2.5% of the total US energy consumption. And the crude distillation accounts for 30 to 40% of the energy consumption on a typical petroleum and refining plant. Okay, and with that, if 81.6, roughly 82 million barrels of crude are processed every day, and it consumes 2% of the crude oil is consumed in the separation, in the crude distillation itself. So for every 100 barrel, 2 barrel goes towards the distillation. So the way it is like if you were to reduce the energy consumption by 15%, it could all over the world, if you were implemented, you could save 245,000 barrels per day. So the impact could be quite humongous. So what happened was that around 7-8 years ago, we got together with ExxonMobil, and in collaboration, we developed we used the method, we developed the method, and we used the method, and that's what I will be sharing with you folks, okay? So what does the crude distillation looks like, okay? So the crude distillation is basically, as you see from this screen, like, comes the crude feed, and it separates a feed into 7 components from light ends, light naphtha, heavy naphtha, kerosene, light gas oil, heavy gas oil, and of course the residue, okay? And so the overview of the method which we employed was, first we collected all the problem data, meaning crude oil information. We estimated their physical properties. We simplified the base flow sheet. Then we generated the search space, all possible configurations. Then we used some reasoning for retrofitting. We reduced the search space, optimized the model, and then we walked backwards and generated the final flow sheets. So that's what I will be taking you through. Okay, so the first step was, here is a crude distillation, how it looks like, which is what was given to us by the team at ExxonMobil. And what you find is that the crude oil comes here in a pre-fractionator. It is distilled, and there's a heater at the bottom, and this is the atmospheric distillation column, and these are the side strippers, and these are the things where light end and light naphtha are produced, and the rest of the components are produced. As I said earlier, this is heavy naphtha, kerosene, light gas oil, heavy gas oil, and the rest. So you can see there are 1, 2, 3, 4, 5, 6, 7 products. Okay. And so what we did was, in order to simulate and understand what is happening in the process, we simplified the flow sheets. And so for a given distillation, generally there's a condenser, separator, then pump the liquid to the column, and then the reboiler and so forth. But in my representation, I will just show the distillation column as a very simple system with a condenser at the top, reboiler at the bottom, and the condenser is solid, and the reboiler is a hollow actually. That's the only difference, okay? And the crude distillation uses side stripper and the side draw. It does not use a side rectifier, but we did include on search space side rectifiers, okay? And so that was the introducing the crude oil. Now let's get down to the method which we used to distill this thing. So of course, like what happens is crude distillation, crude has hundreds of species, and so it has to be lumped into 7 fractions, which is what you see in the right. So that's what we did. We lumped into 7. So we as you see, A, B, C, D, E, F, G, 7. So we pretended that the crude is lumped into 7 parts, and so it is a 7-component distillation. And if it is a 7-component distillation, there will be 6 columns which will be needed to perform the distillation. So here are again, crude distillation flow sheet is quite complex. As you can see, there's a pump arounds, like, there are a couple of pump arounds for the cooling, and steam is injected at various locations and so forth. And simulation of such a flow sheet is quite tedious and very time consuming, and it is not conducive to optimization. So with that, what we did was we began to simplify the flow sheets, which will be amenable to the optimization. So on the left, you see the actual crude distillation. And what we did was we simplified it by removing all the steam injections with the reboilers, okay, as you see on the right side, and also the reboiler at the bottom furnace, which heats the residue, which is shown here. So we simplified the flow sheet, and all these light ends and light naphtha and all those are represented as A, B, C, D, E, F, G, okay? So as you can see, the first step is to simplify the flow sheet. And then what happens is that all the methods which are so far there, like for the synthesis, they produce pure products. But of course, crude is not pure product, as we said earlier. So all these fractions which are produced here, they do allow the other heavy components. So what we did was we said we will allow that. So for example, the light naphtha, which is B, it also can have some A, which is light ends, and it can also have some heavy naphtha components. So we allowed for some impurities to be present. And as you can see again, like kerosene, for example, which is product 4, it could have some heavy naphtha, and it could have some light gas oil. So this way we allowed the adjacent components to be present. And for that, we had to modify our interpretation. So what was in the literature prior to this, all the pure components, we simplified that and we added the possibility of the lighter or the heavier adjacent components being present in the product stream. Okay. And then we synthesized the search space. And for search space, we included all the sharp splits, meaning A and B are totally separated from each other. And we also included thermally coupled sharp splits, meaning the vapor from one column goes to the next column, and the liquid from the next column provides the reflux. So it doesn't. And so what happens is there's no reball or a condenser here on these two-way thermal coupling systems. We also allowed for the sloppy split, meaning a component is overlaps between the top and the bottom of the distillation column. For example, on this one, component B overlaps between the distillate and the bottom product. And again, the thermal coupling is also allowed in these sloppy split configurations. And we use the method, and then by doing that, we can take the column arrangement, which I already showed you. We rearrange the column because the way it was drawn from the simplification from the actual crude distillation. Again, this is not amenable to the methods which are used for optimization. So it is redrawn on the right-hand side and in a simplified manner, as I told you, with the condensers and the reballers. And what you notice is that basically the configuration on the right is exactly the same as the left as far as the energy performance is concerned. Those are two equivalent column configurations, and you can easily draw them by moving the sections. For example, like you could certainly like take this side and move everything underneath here to the left, and then move this everything on the top to the right on CD, and then you will get this column and so forth and so forth. Okay, and this was published a long time ago, so you can see that the advantage of this is now every column has a bottom and the top, bottom and top, bottom and top, bottom and top. So it is much easier to model. Okay. And then we use Shah and Agrawal's method to draw all possible configurations. Basically, in this method, in a matrix, you represent all the streams, and if the streams are present, they are 1. If they are not, then they are 0. And by assigning different streams, you can generate all possible column configurations. And when you do that, for crude distillation, remember I told you there are 7 products now, and for that there are roughly 85 million ways in which you can arrange these 6 distillation columns and find what's the most optimal. Okay, so what we did was we took that method and we simply added to that method, like as I said earlier, possibility of presence of adjacent components. Okay, and then what we did was we added this, and so the impure search space did not change because we still use the Shah and Agrawal method with only this possibility. So still there would be like 85 million configurations to solve, with the only exception that the formulation now has to allow for the adjacent components. Okay. Now what happens is the 85 million is too large, and it generates many configurations, which we were told by ExxonMobil that will not be of any use because they may not be able to build it and operate it. And they wanted something which looks very much like what is in existence. And there are some constraints. For example, the residue at the bottom is not allowed to go from one column to another column. So that's a constraint. Maximum temperature of the gas-fired heater was fixed. Okay. And avoiding any recycle, they said was not acceptable. And the operational preferences for the stream phase, and they said to limit the complexity. So we put all these constraints in the formulation, and these are filters. And when you use that, the search space was reduced to 5,432 configurations. By the way, that is still a very large number to go and find the optimal configuration. Okay. And then they wanted to ensure that some of the existing systems could be used, specifically that the top, the A and B, so knockout drum and all, they wanted to retain that depentanizer and the water recycle. So what we did was we took all that and included it just by a simple column A to B. Okay, so what you say is this whole configuration is now converted to what is shown on the right side. The left is the actual one, the right is the simplified one. And then normally what one would do is for these simulations, one would use the process synthesis heuristics to solve it. Okay. But the difficulty in using heuristics is that a feasible set of operating conditions is very difficult to get. So for any given configuration, what is the split of the components between the top and the bottom is almost very time consuming and tedious even for simple systems. And there's no way one converges to the global optimality. And of course, the over 5,000 configurations, and therefore the problem is quite complex to be solved by any heuristic. So What we did was we generated all those 5,000 plus configurations, and then we used our shortcut optimization model, and then we did some candidate selection from the configurations, handful of them, and then we did the detailed optimization. And so how did we do our formulation? So what does our formulation looks like? So we used our earlier formulation, but we made a lot of changes for crude distillation. So in the past, what we have been doing is we have been minimizing the total reboiler vapor flow rate between all the reboilers, okay? And thermal couplings were obviously allowed, and we do mass and vapor balances everywhere, and we use Underwood's equation to calculate the minimum heat duty in each one of them. And of course, the final products are pure components in the past, but now we will not do that, right? So what are the assumptions of the original shortcut models, like constant relative volatilities, non-azeotropic mixture, uniform pressure, and the usual McCabe-Thiele assumptions of the constant latent heats and every component having an equal latent heat, leading to constant molar overflow. But this model, by the way, works pretty well, as we showed in one of our publications. For example, for a 4-component mixture, there are 18 possible ways the 3 distillation columns can be arranged. And the goal is to find the most optimal one. And for example, if you took a 4-component mixture of butane and pentane and heptane and octane, and if you were to simulate that with the composition shown at the bottom of the screen, what you find is different configurations have different energy consumption. And this is the vapor duty, total vapor duty shown in the rectangles, and the model ranks these very quickly. Like, you run and you find, and then you can do a detailed Aspen simulation, which is what we did, which took a couple of months, by the way, just for these 18 configurations. It took us close to 5 to 6 months to get the optimal for each, because we had to do really sensitivity analysis. So that tells you how complex is the optimization using a detailed process book. And the reason for that is basically to calculate the split of the flows between components which are overlapping. For example, like AB and BCD, how do you find what is the split between the B and so forth? And BC and BCD, and how do you find the correct split between BC and CD? That's what makes it so complex. But nevertheless, the shortcut model worked very well. And as you can see, the process simulation, the shortcut model is on the left, on the right, and the process simulation, which is the Aspen, gives the sequencing on the right. And the sequencing is quite good, actually, and they're into different phases, okay? However, we still wanted to modify that for crude distillation, because there's a great deal of variation in the relative volatilities between those 100 components. So assumption that components has a constant relative volatilities, we challenge that. The assumption that components have same latent heat, we challenge that, okay? And restriction that products are pure, we challenge that. And not using condenser. And we allowed for some heat integration between the reboilers and condensers. So how did we do that? So the first thing was we took the relative volatilities and we said, well, this is the vapor liquid equilibrium, the actual vapor liquid equilibrium. So we did not treat it as relative volatility being calculated either at the feed or the product ends, none of that. We pretended that this is the real equation. And so what happens is becomes our surrogate VLE model, and we fit that to the actual vapor liquid equilibrium data while minimizing the error in the prediction. And that's how we calculate the relative volatilities now. Okay, so it really predicts very nicely the vapor liquid equilibrium in all the distillation columns. And the second assumption we relaxed was that the components can have unequal latent heats. And what the way it is done is through this transformation, which is shown here. And using the latent heat, lambdas are the latent heats of component I, and Fi is the flow rate of the component I, and F. So you can modify each of these pseudo flow rates, pseudo components, compositions by assigning the latent heat values. And now what happens is the assumption of constant molar overflow is no longer needed, and unequal latent heats can be accounted for. And now, rather than minimizing the reboiler heat duty, now we minimize the actual heat duty for each of the distillation columns, okay? And then what we did was for the products, like as I said, like for brownfield application, new products must be similar to the base case, right? Because if you're already doing a distillation of the crude, you don't want your product compositions to change significantly. And therefore, what that means is the products must remain the same phase. But we did allow some tolerance between the existing distillation column flow rates and the new distillation column flow rates. And those epsilons are the tolerance between the new what would be calculated, what was the base case, and a little bit less than base case, and a little bit higher than base case. We did that for the recoveries, and we did that for the purities and the impurities. Okay, so some leeway is allowed in the variation in the flow rates, as long as the recoveries are maintained and the purities are maintained within some tolerance. And then we developed a new method, like the shortcut method, to allow for the heat integration between the reboilers and the condensers. What that means is, for example, this condenser ABC could produce the boil up in B, right? And this is possible as long as the bubble point temperature of this mixture, the vapor which is coming from column 1, okay, is higher than the saturation temperature of the component B. So as long as ABC vapor is warmer, it can transfer the heat here, so we don't need an external heat source. And so in the model, how do we check that? So we came up with a new method. We defined a term called beta, which is the reduced relative volatility. And as long as the beta of this stream ABC is less than the beta of the stream B, this temperature is justified, and we provided a proof of this. So now what that meant was that in the optimization, as long as we know the compositions, we can calculate the betas, and therefore we know whether the two integrations are allowed or not. So we could allow for the heat integrations, and then we also put some additional constraints related to what were given to us, and the residue must be in the liquid phase, and the upper limit on the temperature of the gas-fired heater was given to us, and light ends portion on the top must be in the vapor phase. Using all that, we optimize the problem. We optimize the Q total. Okay, as I told you, now we are optimizing the actual heat duty. And while accounting for the unequal latent heats, impurities in the products are allowed, because as you can see, B output have A and C, and the heat integration between the condensers are allowed. And so what happened now, the model has become much better because the vapor liquid equilibrium is a surrogate of the true VLE, okay? And also there's no more assumption of the constant molar overflow. We have a constant heat transport, and we use those assumptions, and we use that optimization model then to optimize, okay? And for optimization, what we did was, and I will show you some of the results now. And so the results are here, okay? So what you find is that the configurations, all 5,432 configurations were solved using the model. And what we find is that only 465 configurations within the constraints and which were given to us would consume lower heat duty than the existing crude distillation. And the beautiful part of our optimization routine is as you can see that almost all of them converged. And 2,732 infeasible means that these configurations cannot meet the process specifications which were being imposed, meaning like either the purity is violated, or the flow rate is violated, or the recovery is violated. But the ones who converged, and from those converged, we identified 465 configurations. Okay. And so here I will show you the results of only 2, because now out of these 465 configurations, we have to take a handful of configuration and check with detailed Aspen simulation to make sure that what we are predicting is correct, right? Because the model has gone in and has simulated all those 5,000 plus configurations and has given us a small subset of the configuration which it claims to be better than the crude distillation, right? So we picked only 2 because I have to tell you that each one of these configurations to simulate in Aspen Plus took us like a good amount of 4 to 6 months. Okay, so and that gives you the magnitude of the problem which is involved here, right? So I'm just going to show you 2 candidates, candidate 1, candidate 2. Okay, and candidate 1 from our shortcut model says that it should have 17% reduction in the heat duty. Candidate 2 says that we should have a 16% reduction in heat duty compared to the base crude, meaning the current crude distillation. And so what we did was now we have to walk backwards, meaning take the simplified flow sheet and create the actual crude distillation, how it would look like. So now we are walking backwards. So we take the simplified configuration, draw the actual configuration, like, as is shown on the right, okay, by moving all the different column sections. And then what we do is after we have done that, like, we as you see, candidate 1 and candidate 2, okay, and now you see a couple of things here. The first thing you notice is that suddenly candidate 1 has a side rectifier as against the current configurations which only have the side strippers, okay, and it moved the C being on the side rectifier and D as a side draw. Okay, so it did make changes to the flow sheet, like in the skeletal changes in what we call, and it also in the candidate 2 it says that D should be produced as a side stream and C should come out of the stripper. So that was interesting. Okay, And then what we did was, of course, we took simplified candidate 1, we further converted it to detailed configuration with all the steam injections. So basically replacing the reboiler for E, for example, with a steam. And so this now configuration is equivalent. If you were to build it, this is how it would look on the right side. So we look, so as you can see, we are walking now from, so we took the actual, we simplified flow sheets. Now we are taking the simplified flow sheet and creating the actual distillation configuration, okay? And then it was simulated in Aspen, as I said, and along with that, the heat exchanger network, when the feed comes, we had to even simulate the front crude because there's a pump around where there's a heat integration. Now the pump arounds are at different location. So we had to go back and work on the heat exchanger network in the front also, so that it is in line with what is being drawn and the distillation column. So both of them were optimized in Aspen together. And what we find is that the detailed simulation means detailed Aspen simulations. And what we find is candidate 1, the actual savings from the as predicted by Aspen is 15%, as against the shortcut model, which was 17%. So we are very happy because it shows that all the modifications we have made in this large search space, we can find 2 distillation configurations which predict the order of magnitude of the savings by the detailed process model to be roughly the same as what we would predict from the shortcut model, because the candidate 2 is 13% savings, heating duty savings compared to the detailed simulation. And both of them give, of course, the carbon dioxide emission, also equivalent carbon dioxide emission is reduced. So the power of the method is pretty nice, actually. And all the product streams which are produced, they also meet all the specifications, like, for example, ASTM-D at 86 temperatures were met. And these are the variations for the candidate 1. As you can see, the deviations are really small, like the maximum deviation is 10% in the flow rates, and the average is 5%. So that's pretty good, actually. So as I said, to sum up on this side, like the base case, like you take the base case flow sheet, like, you simplify the flow sheet and you redraw it in equivalent configuration with column rearrangement. So each column produces only one product and at the top and one product at the bottom. Then you optimize it in the shortcut model with what I described to you, find the candidates, now walk backwards, arrange all these in the way that normally the crude distillation column looks like. And then finally with all the pump back rounds and steam injections. So you would convert that, and now you do a detailed modeling of this configuration. So what you can see is from 5,000 plus, actually 85 million came to 5,000 plus, and from those 5,000 plus, we can go and find the configurations which are quite useful. Okay. So I had something on the heat pumps, but I think probably two minutes are remaining. So what I will just simply tell you that maybe I should skip, but basically what I wanted to tell you is the heat pumps are something new, like in terms of possibilities to improve the efficiency of the distillation columns. And when we are developing a model for the heat pumps as pertaining to the multi-component distillation. And if you look at for the ternary, just to give you the feel for how complex this problem is, like a 3-component distillation uses 2 columns and it has multiple reboilers and condensers, right? Each column has a reboiler and a condenser, and what happens is the pump arounds can be heat pumps could be between any reboiler or any condenser. And when you use that, and I'll just show you just a glimpse actually, more than anything else. If you consider a ternary mixture of pentane, hexane, and heptane, and you go and you try to find what is the optimal heat pump, and the answer is dependent on the feed composition, and there are many answers actually. And as you can see on this triangular diagram, pentane is this side, pentane is the lighter component, and hexane is on the top, and the heavier component, heptane, is here on the bottom left. And you can see that different configurations are with the heat pumps, and heat pumps are actually shown in blue. So for example, if you look at this configuration, the heat from the distillation column A is pumped to the heat pump to the feed, and there's a heat integration between the B and the A, because pressure is increased on the second column. So what that means is that the vapor B can boil the bottom of the first column, and so forth and so forth. And you can see, and this is valid in this zone, actually, it's the most energy efficient. And if you were to do in this zone, what you find is now it has changed, because now B still was BC, but the heat pump is between the top of the second column to the bottom of the to the bottom of the first column rather than to the feed. So, and you can, and so forth and so forth. So basically, I just wanted to give you a glimpse, like in the sense that when you are looking at the heat pump, depending on the feed compositions, and so the optimization problem is really quite a bit challenging actually than it looks. But nevertheless, the energy savings could be quite large depending on your composition. And if the middle component is high, that gives you the highest energy savings. And as you go towards the bottom, the savings does decrease. So the choice of the heat pump coupled with the choice of the distillation column sequencing and for the feed compositions makes the problem quite interesting actually. And the bottom line message I wanted to give you here is heat pumps should consider intercolumn heat integration. Otherwise, the heat duties are quite large. And column configurations changes with the feed composition and possibilities grow very quickly with the increase in the number of components in the feed. And the problem is even more challenging than the earlier crude distillation problem, which I described to you. Okay, so in closing, okay, new configurations have the potential to lower the energy consumptions, but the process of identifying attractive ones has many challenges, okay, it is quite challenging. And we have developed a shortcut model which does capture the relevant physics of the problem. And we have gone through a lot of extension to include to modify the vapor liquid equilibrium curve and representation, and also to include the changes in the latent heats between the components. And also we calculate the heat duties now, and we calculate the heat integrations between the reboilers and condensers. And we allow for the adjacent components to be present in any product stream. And with all those modifications, our algorithm works extremely well. And we took a very complex problem of the crude distillation, which is probably one of the most complex distillation problem which one can imagine. And we showed that it is possible to find a handful of configurations with substantial reduction in the energy and carbon dioxide emissions. And finally, I just wanted to tell you that we have begun to work on the heat pumps for the multi-component, and that problem is very exciting because it has many possibilities. And with that, I would like to thank my team, the graduate students who did most of the work which I presented to you. And with that, finally, to all of you, thanks a lot for coming and listening to this presentation. Thank you.
Thank you, Rakesh. I don't think there's that much time for questions, but there are two questions. And I would like to, oh, there's more coming, but I would like to ask the question that Adam Aryan proposed, because I also had a related question, and his question was, how would you take into account constraints imposed by column internals?
Okay.
And I think I would like to add to that also the constraint that you would not put a heat exchanger for a 2 degree Kelvin different delta T, but you would want to have an integration where the temperature Kelvin.
What was the last thing you said?
Yeah, like your heat integration, you would want to have a constraint that the difference needs to be at least more than, say, 10 degrees instead.
Yeah, so Harry, that's actually something which is a choice you feed in the program actually. So we have run it with 5 degrees, 10 degrees, and so forth. So it is not something which we, that is at the discretion of the person who's doing the optimization.
And can you also add the different efficiencies in the different columns?
And by efficiencies, you mean the section efficiencies? Or?
Yeah, it basically takes into account the constraints that the column internals pose. Okay,
so in this case, like, in our simulations, we did not take the column internals while making the optimization into account. However, when the Aspen simulations were done, they were taken into account.
Okay.
Because the Aspen simulations were done with quite care actually, and they were very time consuming, very tedious, by the way.
Yeah. And how did ExxonMobil react when you told them that you had to put a stripper upside down and make it into a rectifier? How did they react?
No, that's their confidential information. I just cannot.
Okay, because that's I think it's an eye opener to me, because I actually think you're right in the sense that we have always been looking at it in a very conventional way, and I really like this approach. Yeah, thank you very much for the talk. I think we need to move on to the next talk.
Okay, thank you, Harry. Thank you, everyone. Bye now.
Okay, the next talk is by Kai Kruber, who's filling in from Mirko Szyborski. Kai is a postdoc at Hamburg University, who did his PhD last year on optimization-based design of solvent-based processes, and is continuing his work. Kai, Kai, go ahead.
Yeah, thank you very much for the kind introduction, and hello everyone, and welcome to my presentation. As you've already heard, I'm here in place of Professor Skiborowski, who sadly couldn't join us today. But yeah, I do my best to serve you as a substitute presenter today. Okay, we already have heard a little bit about the assumption of constant relative volatilities, but just to give you a short introduction, as we all know, there are mixtures that act closer to ideality. For example, benzene and toluene, where the assumption of a constant relative volatility is certainly valid. And for example, the mixture of acetone and water, where we can directly see that this assumption maybe not be used in a simulation or optimization, because in the end, the implication is that our best solution, whatever that might be, or our best process configuration, is highly dependent on the assumptions we take and may differ for ideal and non-ideal systems. And just to draw the full picture, as we're all aware of, fully distillation-based separation is not possible for azeotropic mixtures. Here, as an example, isopropanol and water. And this imposes new challenges for the separation, like thermodynamic modifications, pressure swing distillation, extractive distillation or azeotropic distillation, and the consideration of hybrid processes like membrane distillation processes or extraction, and sometimes combinations like heteroazeotropic distillation, where we face new challenges as the processes get more and more complex and interconnected. So if we take a look at, for example, heteroazeotropic distillation, we already see that we have, even for a ternary mixture, a quite complex mixture topology with 4 azeotropes and 3 distillation regions. And we see here that the process is operating actually in 2 different distillation regions. And this makes the design at least challenging. So the generation of flow sheet candidates is very challenging. On top of that, we need to account for the choice of a mass separating agent to enable an efficient process design. And also in terms of optimization and process intensification, this is at least challenging. So there's a need for systematic tools that support us in the process of designing these non-ideal separation processes. One way, so we already heard about the heat pump assisted part. So one way to look at this is the energy efficiency. We oftentimes look at process costs or the pure energy intake of the process, but the energy efficiency, especially for distillation, is a very interesting measure to rate our process and how well our process performs. So the energy efficiency is the ratio of the minimum energy or the minimum work to separate our mixture divided by the actual work of the process. So the minimum work is usually the Gibbs energy of the mixture. And if we take a look at the efficiency for the previous example of an almost ideal benzene and toluene mixture, we can see for a varying feed concentration, which is shown on the x-axis, that we have a huge potential and energy efficiency. And especially in this gray area here, we see that our internal efficiency, so without the consideration of losses in the heat exchangers, we can reach efficiencies of up to 70% for this example. If we now consider the heat losses or exergy losses actually in the heat exchanger, so in the condenser and the reboiler with 10 or 20 degrees, we already see that here the efficiency drops quite far. And if we now take a look also at wasting our energy that is taken out of the system in the condenser, then we go even below 20% efficiency. One way to increase this again is the use of a heat pump in that situation. So we can use a vapor recompression in here to increase back the energy efficiency. And here we have an energy efficiency for a feed in the gray area of up to 35%, which is a considerably good value. But this, of course, highly depends on the mixture, as we have here only 30 or 31 Kelvin in difference of our boiling temperatures of the pure components, which leads us to pretty high coefficient of performance. If we now take a closer look at a non-ideal system, here the example of acetone and water, then we see that we have considerably lower efficiencies for the internal efficiency of almost 38%, and this drops even further with the external efficiencies. And if we take a look here for the vapor recompression, we can increase it a little bit compared to the external one, where we do not consider our condenser heat to be used in the process, but we cannot surpass here our 20%. And actually, with increasing acetone composition in the feed, we drop quite significantly in energy efficiency here. So why is this the case? If we take a closer look at the binary mixture here for acetone and water, we see that we exhibit a tangent pinch at the top of the column, so at high acetone compositions. And this limits basically our operating window and our efficiency that we can reach here. For the simple column, we now picked for comparison an internal and an external efficiency and showed them on the bottom. The external efficiency now does not consider a fixed delta T, but rather a chosen steam level, a pressure level of steam for heating the reboiler. And we can see here that we only have a efficiency of 8.7%. If we take into account the heuristics that you learn at the university or that are very common in distillation practices, then we see that a relative volatility above 1.3, maybe 1.4, 1.2 should be enough, but we see at even high concentrations of acetone, we have our relative volatility of 1.3, but still the efficiency of the process is really low here. If we now take a look at the vapor recompression for this simple example, then we can see that we can increase the efficiency a little bit, but not too much compared to our external efficiency of 8.7%, which is due to the tangent pinch at this point. So what can we do to improve that? If we now take a look at intermediate heat exchangers in the column, and in this case, intermediate reboilers that are evaporating part of the downcoming liquid in the column, then we can see that we can, at least our internal efficiency, that we can increase it. So we can almost double it compared to the simple column. And yes, you already see that here is a reboiler located above the feed location, which is pretty uncommon. But what we also see is that the external efficiency drops further to 6.3%. This is just due to the fact that we need more energy input here compared to the simple column, and we considered the same heat duty for all the heat exchanges. Not the heat duty, I'm sorry, but the same utility stream for all the heat exchanges. The interesting part comes when we now take a look at the level or the temperature level at which the biggest amount of energy is given to the column. So this is now at 59 degrees Celsius, which is only roughly 3 degrees Celsius higher than our condenser temperature, which is a very interesting opportunity then to reconsider the vapor recompression step here. So what we did is we took a look at a vapor recompression for the 2 intermediate heat exchangers. And what we now see is this is a very interesting opportunity. The external efficiency here of the process can rise to 20%. And what we see, the coefficients of performance of our 2 compressors or heat pumps is pretty high, and we have pretty low compression ratios. So looking at this result, we asked ourselves if this is really valid, and tried to validate this in Aspen Plus, and that this worked pretty fine. We have a good agreement in thermodynamic efficiency. So we saw this as a great opportunity to rethink the design of intermediate heat exchangers here. The next logical question for us was to take a look in the literature if this was proposed somewhere. And in the past 25 years, we couldn't find a single publication here, but prior to that, we found something in 1986 and 1996. The last one is by the previous speaker of today's session. And already in that time, it was suggested to heat above the feet, and also to consider maybe for the low temperature heat source that's needed there, to consider heat pumps. But again, also here a quote of the publication of 1996. It is against the widely accepted normal distillation practice. So if we take a look over the full range of acetone compositions in the feed, we can even see that the vapor recompression or the heat pump assisted process with side reboilers gives us an even higher efficiency compared to the internal efficiency of the simple column. This is very interesting. But no doubt to build the process, this will get a little bit more complex. So of course we have to integrate our heat pumps, our vapor recompression in the process, but also we have to take into account that the vapor load in the different sections varies quite a lot. So we need to adjust the diameter in these parts. If we take a look at another example, then we can see directly for water and gamma valerolactone that there's a very poor efficiency of at most 10% with respect to the internal efficiency. This looks even worse for the external efficiency. So even with vapor recompression, we are not able to push this really far. And this is mainly, again, due to a tangent pinch that occurs for high water concentrations. Although we have a pretty reasonable relative volatility in the high water content areas, but the process efficiency is determined by that. And we also have in our assumptions a feed that is an aqueous solution of GVL with only 5% gamma-valerolactone. And yeah, for that reason, we have the poor efficiency of the distillation column, since we have a very high distillate to feed ratio, and of course the tangent pinch in the rectifying section. So in this case, it makes total sense to think about hybrid processes and to combine the distillation column with different unit operations. And in this case, we picked a few of them as an example. So membrane-assisted distillation processes, extraction, heteroazeotropic distillation, or extractive distillation. And our selection has in common that we often need to select an optimal mass separating agent to get an economic and ecologic performance of the process. This is, of course, especially interesting for our system, and as you may already know, is for these highly diluted aqueous solutions, liquid-liquid extraction is of is very interesting for these processes. So the challenge here, like I said, is of course first to find a suitable solvent, and in the best scenario, the optimal solvent. So what you can do is go to a solvent database, select and test with a few models. But in recent years, it gets more and more prominent to fill these solvent database with predictive thermodynamic models, which is a great opportunity, but also increases the search space tremendously. That's why at the university at Aachen, they thought about investigating 5,000 solvents for the shown case study that they did it, or they used as a model, a shortcut model for the extraction column and the distillation column. So they took a look at the minimum solvent amount that's needed to perform the separation and the minimum energy intake for the distillation column. The shortcut offers, of course, the opportunity that the calculations are very fast and you can easily take a look at thousands of solvents here. But nonetheless, it has some crucial assumptions that with a detailed look at the process should be omitted at some point. So what we did is we took the results coming from Aachen and made a rigorous optimization for the process. And we closed the recycle, formulated a superstructure optimization model, and took a look at promising solvent candidates here. And the benchmark solvent butyl acetate, compared to that, we could really improve the total annualized cost here of roughly 50%. This is a great example of integrating different levels of details in the models. What we see compared to the simple distillation column is that we have a huge saving potential here for our benchmark solvent and also for the solvent toluene, for example. We can see that we save energy and total annualized cost in the comparison. So distillation, as already indicated by the energy efficiency, is not a suitable case for this part. We even further thought about how to enlarge the process and even improve it, and came across the idea that we could pre-concentrate our feed by a membrane process, because membrane processes are very well suited for the concentration of aqueous diluted streams in here. So what we first checked is, with our existing model, is there a potential, and how big is the potential when we decrease the mole fraction in the feed to the liquid-liquid extraction column? And we saw a great benefit there, so we continued. And again, we took a theoretical idea to check what's the potential, or if it's even feasible to use a membrane in that sense. So we analyzed the driving force for different permeate concentrations of gamma-valerolactone, which you can see on the y-axis, and retentate concentrations on the x-axis. And you can basically see here the different pressure lines or the osmotic pressures that need to be surpassed to fulfill a separation here. The red area shows basically the restriction that we had for the most common membranes that we considered. But you can see here that up to 10 or 12 mole percent of gamma valerolactone in the retentate phase, we have a pretty reasonable process window here. So what we did next are experiments for a membrane screening, and then later on decided on a nanopro membrane here that served as well as a pre-concentration step so that we could even further decrease the energy intake up to 10% compared to our toluene case, and the cost even further. So here are some questions obviously remaining. So what are we doing with the streams that are leaving the membrane or the extraction column? So we can use our existing tools and further develop them to go ahead here. If we come now to an example considering the separation of azeotropic mixtures, I want to show you something that we investigated for extractive distillation columns. So here, very comparable to the liquid-liquid extraction, we have the solvent selection. That again, we can do by looking at databases or enriched databases by predictive thermodynamics and try to choose an optimal solvent. We still have the challenge of the process design itself. So again, here we have an optimization of a superstructure model. But since both columns or both unit operations are distillation-based, we have also a considerable amount of heat integration that we can do. So we can save a lot of energy here. So what we considered was the simple heat integration, the thermally coupled variants, which you see on the left, and also a heat pump assisted process, in that sense, a vapor recompression for either column that's possible. We could have potentially put all this together in a big superstructure model and see what the results are, but this would blow up the problem tremendously and make it very, very, very hard to solve. So what we did is we did a hybrid optimization method. So we coupled an evolutionary algorithm together with our local deterministic optimization in GAMS. And in each generation or for each individual, the evolutionary algorithm defines the solvent selection. So it selects one solvent, it selects one process intensification method, and gives initial starting values for the feed stages and the total number of stages of the different columns. So, and in the different generations or for the different individuals, we get back the fully optimized, locally optimized process here with an optimal design, also with the information of the total annualized cost. For the case study of acetone and methanol separation, you can see here the results, how they vary over the generations. So the generations are depicted on the x-axis and the total annualized cost on the y-axis. We can see two main things here. So first, the evolutionary algorithm works as expected. So we have a diversity in the first generations, and then later on we focus on a water-based process with different process intensification methods. So this works successfully. What the second point that is also interesting is that we only need 8 generations here, or we only have 8 generations, which is comparably low to other applications of evolutionary algorithms. This is due to the fact that our individuals get refined by the local optimization procedure. So each individual is from a local perspective, an optimal process. So yeah, the starting values are provided by the evolutionary algorithm, and optimal results are gained back to consider as the fitness function. If we plot the same results in a little bit different way, then we see the second opportunity that we have with this methodology. So we see the operating cost on the x-axis and the annualized investment cost on the y-axis. And what we see is that without formulating a multi-objective optimization problem, we receive an approximation of something that looks quite similar to a Pareto front. So this is also very interesting. And just to remind you, all the points that are shown here are locally optimized, rigorously optimized process configurations. As a final slide, I want to give you an even more detailed insight into the results here. If we now consider all the best combinations that occur throughout the evolutionary algorithm execution, we see that if we only would consider the sequential step of selecting a solvent, so we take a look at the conventional processes, we would see that DMSOs may be the best candidate. And then we would consider in the next step the means for energy integration. Then we would realize that only the conventional process should be used in that case. But we would completely miss what we see if we do this examination in a simultaneous way. So we have all the information at hand in the same step and see that the simple heat integration of a water-based process can save even more in terms of the total annualized cost. So what I've shown you is a different way of seeing the processes, basically an exergy-based or as an objective, the thermodynamic efficiency. We can get some valuable insights here, how we can increase the process performance or what we have as opportunities for energy integration. I also showed you a few examples here for the hybrid separation processes and the challenges that go along with it. So we need to consider, for example, the selection of a mass separating agent, the process configuration, and also the intensification all in one step. But we can significantly improve the processes here that already exist. And maybe as a very brief outlook for, and also as an advertisement for the software tools and everything, and elaborated models that are out there. On top of that, we can do very, very interesting things to improve and further achieve improvements here. So we could think about flow sheet synthesis and design of machine learning approaches to even get more out of these very valuable process models. And with that, I want to thank you for your attention.
Thank you, Kai. We have one question, an anonymous question, which I think is actually a very good one. The remark is that normally vapor recompression is applied for systems with about 20 degrees C temperature lift, but in your case you showed one with 100.
Yes.
And the coefficient of performance is still 4.5. The question is how is that achieved?
So a very good question. We are aware of the fact that this is a pretty tough or challenging, would be a very, very challenging vapor recompression here in that case, but we don't want it to limit our opportunities right up front. That's the first case. The coefficient of performance also depends, of course, on the assumptions that are taken here. So we are calculating the the compressor via an isotropic calculation. So we have an isotropic efficiency of, I think, 80% and 90% mechanical efficiency. And in the end, this leads us to the results that we just saw there. It's arguable if these assumptions are reasonable, but as long as we take them throughout the whole comparison for all the processes, at least qualitatively, we should be able to compare them. Of course, it is a different thing. I wouldn't recommend based on a single picked value here to build a vapor recompression like that. That's a different story.
Okay, I have one more question. Well, one comment, more or thought, and then I would like to move on to Eva. With your initial picture, I saw that you were using VRC, and I was starting to wonder, VRC requires also capital. In some ways, you could either tune or change the vapor state or the feed state more to vapor phase. And also you could consider doing electrical heating, because you can do electrical heating at any temperature level and it doesn't become less efficient. Mm-hmm. And as such, you can maybe move away from the fact that your heating medium is not the place where you apply it. Electricity and electrical heating doesn't have that disadvantage. And I was wondering whether you could extend your formulation for that.
Yes, that's an interesting point. So we haven't considered this yet, but we can definitely do that and consider this in the model. What we can do as well, and what you also mentioned, is the heating or the partial evaporation of the feed. And this was also suggested in the publication by Professor Agrawal. If the reboiler is very close to the feed, it maybe does not make total sense to introduce another heat pump there and another heat exchanger, but just partially evaporating the feed. That's completely true, and with these decisions, we would need to develop further our software tools. But nonetheless, if we have all these opportunities and all this information at hand in an early design phase, we can better decide what to do next, of course. But yeah, a very good point here, and we will consider that in the future.
Okay, I would like to move on to the next talk. The question that is posed, we can also handle at the end. Next in line is Eva Sorensen, and I'll let you introduce the talk yourself to save time. Eva, go ahead.
That's okay. Thank you very much, Harry. So I'm Eva Sorensen. I'm from UCL in London. And I want to tell you a little bit about the work that we have been doing within optimal design and operation of hybrid systems, reactive system, dividing wall system, and hybrid reactive dividing wall systems. So a bit of a mouthful. So what I will be looking at is just a little bit about process intensification first, then a bit about how we've been solving these problems, and then show you some examples of the results. So a bit about process intensification first. We all know distillation is a very energy intensive process. Rakesh outlined that in his talk at the beginning. So what we've focused on in terms of trying to improve these processes is to look at the more novel designs, process intensified designs, where we have a dividing wall column, where we're combining multiple columns into one. We've looked at reactive columns, where we are putting a reaction into the column, as well as hybrid processes. And there are, of course, others that fall under the umbrella of process-intensified distillation, but I will not be covering these here in the interest of time. So in terms of dividing walls, there's been a lot of focus on this over the past couple of decades. They are a great alternative to a standard direct or indirect sequence of separation, whereby we are combining columns. So you could have this as the sloppy split that Rakesh mentioned at the beginning, or we could have this with a Petiluk structure with a pre-fractionator. Or we can put it together into a dividing wall column, whereby you have the separation of a ternary mixture, where you're getting pure components A, B, and C from a single column. Lots of work have shown that this has a good distribution of the middle boiler, because it goes to the top and the bottom on one side of the wall. It's more energy efficient, saves capital and operating costs. But it's a bit difficult to operate here because the vapor splits that we have at the bottom of the column that cannot really be controlled. We control the liquid split at the top, but we can't control the vapor split. And also in the standard sequences, you will have the option of having different pressure in different columns. But in a dividing wall column, you are stuck with, obviously, because it's one shell, the pressure on both sides have to be the same. For reactive distillation, we are taking a reaction and putting it into a column so that we have a reactive zone within the column. This improves conversion, productivity, and selectivity, reduces catalyst amount, reduces energy capital cost. It may also eliminate the need for solvents if we have azeotropes. So a very good alternative for some reactions, but it has a more narrow operating window. We need to have similar temperatures and pressures for both reaction and distillation. And we may need to have quite long catalyst life if we're using heterogeneous catalysts. And we'll need to get the residence time distribution right. Now, we've looked at this quite a lot and used a superstructure solution approach, where we've looked at alternatives of having the traditional approach with the reactor followed by a column, having a pre-reactor, side reactor, having additional columns to deal with some of the separation, and also the option of side strippers. So this superstructure approach is very much how we have considered all of our work. Kai talked a little bit about how they have done it there as well. So it's a fairly similar approach. We've also looked a fair bit at hybrid distillation systems. So that is where we are combining distillation with another process. The one that I'm going to focus on here is looking at combining it with membrane processes, where we integrate these two together. So for azeotropic, for instance, if you have a minimum boiling azeotrope, we can then use the membrane network at the top to cross the azeotropic point, because the membranes are not operated on vapor-liquid equilibrium. The benefit of these processes depend a lot, though, on the availability of a membrane for that particular system and how good that membrane actually is. But they can, as I said, overcome azeotropes, can reduce energy consumption, possibly also operating cost. You can have smaller equipment size. But the membrane system often costs quite a bit, and we have the same issue there in terms of temperature and pressure, that we need to take into account what the membrane can actually tolerate. But looking at potential, say, for energy consumption, if we were to compare a hybrid distillation membrane process with an extractive system. This is just for one example here. For ethanol dehydration, you can see that the heating duty for the hybrid process for a whole range of different systems will still be significantly lower than what you would have for an extractive process. What we then tried to do is to put all of these together into a hybrid reactive dividing wall system. And that is what I'm going to be showing you a little bit later. So what we have here is a reactive zone inside the column. We have the membrane system that helps take into account the azeotrope that we've got, so we can break that. And also there will need to be, for some systems, an additional column to complete the separation. I just want to mention a little bit first, both Rakesh and Kai have talked about how complex these optimization problems can be. We have used GPROMs for the model that we're running with our optimizations, which means we have a very large number of equations, we have a large number of degrees of freedom. So initializing these kind of systems, you can imagine how many degrees of freedom you have in something like this. If you try to do that completely from scratch, it is practically impossible. So what we've tried to do, or what we have done, is to develop a shortcut design method. So not Fensk-Underwood-Gilliland, not McCabe-Thiele, but an optimization-based process where we're decoupling the column or the column sections at the feed point, and then use feed stream information, light and heavy keys, construct that into a shortcut model that is looking particularly at the pinch point where the feed is coming in. And then we define a pinch variable, which is the difference between when we're guessing what the streams should be, what that pinch variable is. And then we just use basic optimization, quite simple, to try to minimize what that difference is. So for a simple binary column, it's obviously only one feed point. If you have a complex column with side streams, lots of other things, then you will minimize the sum of these. This gives us the actual number of stages and actual reflux ratio in the column, but it gives us far more because it also gives us, if you look over here, initial values for all of the streams. And that obviously helps a lot to initialize these optimizations. In terms of the optimizations, what I'm going to be showing you is some examples where we have minimized total annualized cost. Looking at product purities of 99, where for some cases, although not quite all of them, we have equal pressure drop on either side of a dividing wall. You can see the computer specifications here. We've used parallel processes for the optimization with a number of workers, and we've used a stochastic and deterministic optimization approach. So we're using GPROMs for the simulation, which is linked to a foreign object called Multiflash for the VLE. That is then communicating with the actual stochastic optimization software that we've developed. Data handling is through Excel, and the interfaces here are coded in C. The solution methodology we're using, if you're trying to solve these kind of problems with a deterministic approach, you will end up with a lot of failed initializations, even if you've got a good starting point. And if you try to do it stochastically, the solution time is very long. So what we've also tried to do is to do a combined approach, whereby we have an initial, a preliminary, a genetic algorithm solution that takes us quite close to the optimum, but not quite there because of the solution time. And then we use that in, so this is GPROM's deterministic optimization that then gives us the optimal solution. In terms of costing, we're obviously taking into account all the capital costs. We're looking at operating cost, heating, cooling, electricity. And when we're looking at dividing wall columns, we have solved it as a Petley look because that is the thermodynamic equivalent. But in terms of costing, we're then looking at a dividing wall area, which is the sum of the two individual areas. That's what most people have used when they are looking at dividing wall columns. So just a quick note to say that for one example here, if we try to solve a particular optimization with genetic algorithms, you'll end up with quite a long solution time. If you use the combined approach, you'll get some of the way there with the preliminary genetic algorithm, and then you do a very, very quick deterministic solution. You get a much faster answer. I haven't showed any values there for the deterministic only, because that has so much of manual manipulation in order to get it going that it doesn't give a fair comparison. Now we'll look at some dividing wall columns first. I said some of the drawbacks here were the issues around controlling the vapor splits and pressure on either side of the wall. What you can do is to look at reduced vapor transfer. This is something that Rakesh presented about, well, over 20 years ago, where you stretch the wall either to the top or the bottom of the column, and you can also stretch it completely across the column. So rather than having the thermal coupled or the streams, thermally coupled streams at the top and the bottom of the column, you now have a liquid transfer from one side of the column to the other. A drawback is you then do need to have 2 reboilers and 2 condensers, but as we'll see, they may, in some cases, be cheaper than having it as just the standard column. When we're optimizing these, this would be the actual structure that you would build, but in terms of the simulation and the optimization, we are looking at the thermodynamically equivalence of a Petley look arrangement. But as I said, with the costing, we are looking at something that much closer resembles the dividing wall. Here's one example where we have combined, so we looked at a mixture of benzene, toluene, and orthosilane. We have looked at having this as a direct sequence as well as an indirect sequence. The dividing wall columns, the various alternatives with having the wall at the top and the bottom, as well as dragging it all the way across. You can see here the temperature profiles for the different arrangements, and they are obviously very similar. In terms of the column size, you will see that the dividing wall, the different alternatives are very similar. You can also see that the duty or the utilities that are required is less than what we have in the combined of the conventional approaches. And you can also see that the total annualized cost is quite a lot lower for the dividing wall compared to the other sequences. But if you look at the variation between these different dividing wall systems, they're actually not that dissimilar. They're quite similar in this particular case. If we look at the dividing wall again, we can also use vapor recompression, like Kai mentioned. So we can do this just with a standard dividing wall column. You can use it with the wall going from the top to the bottom, which will allow you to vary the pressure on either side of the column. You can also combine these 2 reboilers at the bottom together into one structure. You can split this so that you have a double effect like structure. You can have the vapor recompression on both sides, or you can do the vapor recompression and combine the reboiler and condensers together. So lots of alternatives there that one can try out. In terms of the results for this structure, if we look again at the benzene, toluene, or orthosilane, these are, so that's the standard dividing wall, that's the vapor recompressed, that's the wall going all the way through. Combined reboilers, double effect, vapor recompressed with the wall all the way down, and that's with the combined reboilers. We can see here that for the double effect one, one of the sides of the pressure had a much larger pressure than on the other side of the column. That's the other side of the column. But for all the other cases, the optimum was, or the minimum for the pressure was 1 bar, and all the solutions came out at 1 bar. We can also see that these were more expensive. They came out higher, but the operating costs were lower. Combining all of the structure, the standard or the vapor recompressed ones ended up being cheaper than the other systems. Now, if we then look at, well, how do we separate systems? So we can do a simple ternary system in a dividing wall column, but if we then have an azeotrope, for instance, then we have the issue of being limited by the azeotropic composition. So what we then can do is to add a hybrid, or have this as a hybrid system where we're adding a membrane system in the structure. So we can do this in different ways. We can have the, so this is for a minimum boiling azeotrope. So we can have the membrane network here at the top. So it comes off the condenser drum, goes into a membrane network, and then is recycled back. One stream is taken out. We can have the pervaporation and the distillate or the distillation in a different order. So we do the pervaporation first, or you can have 2 columns, but with a membrane network in the middle, where the job of the membrane is basically just jumping over the azeotropic point, and then you can do the rest of the separation on the other side in the other column. The membrane network we have modeled not just as a minimum membrane area. We've looked at this in terms of like how many stages would you need to have in this membrane network. There will be some heat exchangers and potentially pumps in between, and also how many membranes would you have in each stage, because obviously it doesn't have to be the same in each stage. Now, in the interest of time, I won't show you how we've solved this, because the actual optimization of something like this is quite tricky, because if you have to initialize in the superstructure having all the maximum number of membranes, whilst what you may end up with is of course less than that, but numerically we also need to calculate for the other side. So what we're doing here when we are turning this into a hybrid, we are putting this together like this. So we have the wall to the bottom, and then the membrane network going over the top. And if the example, for instance, was ethyl acetate and acetone with the azeotrope, you'll have the azeotrope going up over the top, and then the product going out through the bottom. And the job of the membrane is to then jump over the azeotropic point, purify the rest of the ethanol, and then sending the retentate back in again. And thereby we are jumping over here. So looking at that particular example, if we look at the various options, so this is showing the results for the distillation followed by pervaporation followed by distillation. You can see the small pictures up here. Then the option of 2 columns with a pervaporation unit in the middle, or the hybrid, which I'll show you the picture of just here. What we'll see is that the membrane networks, if we're doing just distillation and pervaporation either before or after, we need quite a few membrane stages to do this. I haven't shown number of modules per stage, but you can see there's a large number of membrane modules needed. For the hybrid, as well as the where we're just jumping over the azeotropic point, we only need 5, which obviously is a lot less. In terms of costs, you can see that these are less than these. It's a bit less also than the distillation followed by pervaporation, but the hybrid here doesn't really win anything over just having a standard 2 columns and a membrane. Now, I should say at this point that obviously the results that we're getting here depend on the cost of the membrane. And for other examples, also it would also depend on whether you actually have a membrane that can deal with this particular separation. So we've used a fixed price for the membrane here in some of the other work that I won't show here, we've also looked at the impact of the change in that price. Now we can also look at heat integrating the hybrid system. So you can have a vapor recompression, have that on the pre-fractionator side, on the main column side. You can do it on both sides. And comparing those for a binary system, you can see the distribution of the costs that we've got here. You'll see that having the vapor recompression, if you compare it to, so this option here is the standard dividing wall column, and that is the cost. This is the vapor recompressed examples. And you can see here that having vapor recompression on both sides is a saving a significant amount of cost. Now, these two, so having the vapor recompression pre and on both sides, we've also looked at this, whether the, so this is for the hybrid now, for a binary system. When we had binary, the distillation with a per evaporation in middle and then followed by distillation was pretty much the same as the hybrid. Now, if we then have a ternary system, you can imagine having two walls here where you have a withdrawal between the two walls. That's also possible. We have looked at that, but I haven't got time to show you the details of that. And we can see that the total annualized cost then does go down. So having more walls is beneficial in this situation. Now for the final thing that I wanted to show you, which was the hybrid reactive distillation wall column. I'm going to look at a generic reversible reaction system here. So this is a reaction with A plus B goes to C being a product and D being a byproduct, where there is an azeotrope between A and C, and where the boiling point order is that the azeotrope is a minimum boiling. Then C is the light component, lighter than A. D, which is the byproduct, is then next, but then one of the reactants is actually the heaviest component. So this is a bit more complicated. Now, we've used this as a generic example, which means that we have manipulated the thermodynamics in the code so that we get the characteristics that we want to show, because our focus is to consider the relative operation in a standard separation unit versus one of these more complex units. We can obviously also show this for a specific mixture, but then the answers will only be applicable to that particular mixture. We've also considered here different types of kinetics as well, and different types of chemical equilibrium, but I'll just show you one here. Now, because this is a reactive system, we're now changing the total annualized cost. So what we're now looking at is a production-based total annualized cost. So we're taking into account how much product we are actually able to get. The base case that I will look at is the a reactive dividing wall column, which I've shown you here. That's the reactive area in the column. Because of the boiling point order here, we need some additional separation on the following the reactive column. So I've looked here at using pressure swing distillation for that separation. I've also looked here at the difference between the wall in the middle and the wall extended to the bottom. Now, pressure swing is one way of dealing with azeotropes. In this case, we have got a pressure-sensitive azeotrope. So the other option here is to have this as a hybrid process. So here we've got a standard reactive column followed by a hybrid separation, or we can have this in the dividing wall with a wall either in the middle or extended to the bottom. Same as before, when we do this is what the actual configuration would look like. What we're doing in the simulation is the Petli look equivalence of those. So this just shows the degrees of freedom that you have in these sort of optimization problems. Rakesh alluded to this in the beginning. He looked at different types of structures to this, but you end up with an awful lot of degrees of freedom that you need to optimize. So for the hybrid dividing wall, for instance, where we are looking at having the wall in the middle, we have 30 degrees of freedom if we're looking at number of stages, all the reflux ratios, all the alternatives, where the wall is going, etc. So this is quite a big problem. Here's the results for one of the cases where this is the pressure swing examples, and this here is the hybrid. And we can see here that for those who are operating at pressure swing, the second, or that final column has a pressure of about 11 atmosphere. We can also see, if we compare the duties between the hybrid alternatives with the pressure swing alternatives, that hybrid has got much lower energy consumption. So this one is more energy efficient. We can also look here that like-for-like structures. So if we can compare these, you'll see the costs here, that the actual production-based total annualized cost is fairly similar. And the pressure swing alternatives are actually coming out as being marginally better. In terms of like-for-like, so if I'm comparing, for instance, the reactive with the pressure swing, the reactive with the dividing wall, you can see that those are actually quite similar. The same if we're looking at the hybrid ones. So they are also quite similar. So these we could potentially also look at as retrofitting options. So what I hope I've been able to show you is that we have been able to develop a shortcut design method and a combined optimization strategy that greatly improves the feasibility of doing these sort of studies, as well as increasing the efficiency of the optimization. We've explored the designs and operation of various process intensification structures, dividing walls, the hybrids, combining these together until ultimately the hybrid reactive dividing wall system. These process intensified structures are showing great economic potential, especially in terms of energy savings. And by using the vapor recompression, for instance, we can also save additionally based on that. So the heat integration is beneficial. Now, I haven't done this work. Of course, the people who have actually done it are Katerina, Diane, and Fanny. Katerina has been focusing on the reactive part, Diane on hybrid, and Fanny on dividing walls. They've also done this last bit of work together. Diane and Fanny, I've put PhD submitting. They are submitting tomorrow. So this is about as close as you can get to submitting a PhD. So with that, thank you very much for listening. And I'm happy to answer the one question that I can see we've got, Harry.
Oh, we've got more questions.
Do I? Oh, it's gone down. Okay. Do you want to control
the top one, the bottom one? That I like most.
The bottom one. Let's have a look.
It's have you knowledge of actual implementations in industry of hybrid structures?
Hybrid structures with dividing walls. I don't think yet. Do you know of any?
No, not yet with membranes, let's put it this way. We are looking at cases where we would combine, say, extractive distillations with reactive distillations. That, yes, we are. But I would assume also BASF has. But I have not yet, and this is why I wanted to know whether you've heard of membranes, because that was my next question. In your cost comparisons, did you include the cost of replacing the membranes? Because they typically have to be replaced quite
Yes, but
frequently.
I can't remember what the membrane replacement was.
Okay, so but you
yeah,
did
it's
include some.
part of the costing, yeah.
Okay,
Yeah.
because often that's where the uncertainty lies, I think, and that's also often what is causing the barrier or the hurdle to implement these membrane separations. And it doesn't mean that they are no good, but the uncertainty remains then so large that people say, oh, I'll go for the other one.
Yeah, I think what we've tried to do in our work is to show the potential that these processes can have. If there isn't much to gain, then maybe it's better to just stick to what we've got. But if there is high potential, then it might be worth exploring it further as an option. Now, we have looked at pervaporation. I can see there's a question that asks whether vapor permeation could be used. Yes, you could use that as well. It depends on the type of system that you're looking at, which one you would pick.
Yes, and there was another question about the liquid-liquid configuration, whether you see more other examples maybe that could leverage the potential for that solution more?
So I think having the pressure, different pressure on either side, and most of the results we've seen, it's just ended up with the optimum being, let's just stick to the same pressure. But we haven't looked at, we've only looked at certain mixtures. There may be mixtures where this is an option, but if you do have the liquid-liquid configuration, you have the option to try to look at changing the pressure. You would need to take that into account when you look at because with these structures, you've got the transfer of liquid from one side of the wall to the other side. So if the pressure is different, you would need to take that into account.
Yeah, probably you get flashing on one side.
Yeah.
You could, that can be accommodated, but you would have to design for it.
Yeah.
So I have another question. A lot of these configurations you've programmed yourself, and in industry we typically have Aspen or Unison, and then it becomes too much of people to do this and to bridge this gap from solutions like you have, where you use a superstructure and you do this optimization, and when we have to do the actual implementations, we want to re-simulate it in Aspen. Have you done any preparations in making predefined Aspen models that industry could use?
No, I think in terms of software development, our main focus has been around optimization and being able to solve these sort of optimization problems more efficiently. So Janef and Yi have developed some software that is capable of doing that very efficiently. Now, I think it's worth keeping in mind that what we've actually done is to use as a structure the thermodynamically equivalence, which is a petal look arrangement. We have used GPROMs rather than Aspen, but that is also just drag and drop standard columns. So we haven't written mass and energy balances ourselves. We've just used the way that you could do it in Aspen, I guess.
Yes, well,
at least GPROMs can easily handle this.
Yeah, GPROMs is a little bit more flexible in doing the things that what you're doing. I think you would have to use Aspen Custom Modeler or so, I think, to do that.
Yeah, I mean, as you know, we've always used GPROMs, and they're coming out with they have an equivalent now with GPROMs process, which is very good, which we've been using the last few years. So that should be a good alternative to Aspen. I can see that somebody is asking about controllability and startup. If you can consider that during the screening. Controllability, yes, you can, and we have considered control issues, particularly related to reactive distillation. If you are taking into account startup, then the optimization becomes a dynamic optimization problem. It is possible to do, but it becomes quite a bit more complicated, and I wouldn't try to do it with a superstructure approach. I would look at one configuration at the time in that case.
Okay. Maybe it's now time to ask all the people to come back online again. Since I hope that Rakesh is also still there.
No, Rakesh, because of the time difference, the US changed to summertime a week before what we did. So he is actually teaching right now. So he had to leave, unfortunately.
Okay. So because there was still, I think, one question that I had for him. Well, thank you. First, I would like to thank the speakers. Unfortunately, Rakesh is already gone, but thank you for 3 interesting talks. I would like to then bring to the attention that next week, Tuesday, we have another webinar where we will be talking about more on hardware design, on tray columns and on pack columns. You can find that information again on our working party website that I hope you now can find back, EFCE.info, and then try to find your way to the fluid separations working party. With that, I have one last question to both Eva and to Kai. And maybe also Boelo can join in, but I wonder, our current tools, our flow sheet tools that we use in the industry, are they enticing people to come up with the real optimization challenges that the energy transition actually requires us to use? Because a lot of people in the industry are not doing this very well, more complex type of optimizations that have been shown today. But we need to get there in order to save what is it, in 2030 we need to save 30% already.
Yes.
And we really, well, you are all educators. I think you are the ones that need to teach the students now in order for them to facilitate that when they reach industry. But do you feel the tools are readily available, and what should change if they're not?
I think that's a question for the software vendors, isn't it? So the sort of things that I've shown you today, my students are certainly aware of the different options. I don't set it as standard coursework because there isn't room for that within the standard 15 credit module. But those who do it as a research project, they do their own modeling and coding, using the same approaches that I've showed you here. So they will go out as graduates knowing how to do it.
Are you at least showing them at the last course in the year what you can do about what you can do with your tools?
Yeah, we do. In our master's level design project, the capstone design project, we are covering a lot of these things. So we're also looking at things like parameter estimation of kinetics, for instance, if that's where the uncertainty lies. Yes.
Okay. And how is that in Hamburg, Kai? Are you aware?
Yeah, we are more in the transition right now, and we got a lot of inspiration of the Imperial College there, which are a little bit ahead, I would say.
University College, not Imperial College.
University College.
I'm
sorry. Which are a little bit ahead of us, I would say, in terms of the software education or the education to be aware of how to solve these problems. but we have done a lot in the past years, and we have plans for the next years. But we are also on the master's level teaching them a few of our tools, giving them insights, but then of course the proper insights are gained then in the project works, master thesis, and yes.
Yes,
Okay.
in Twente, what we do is we do educate them on dividing wall columns. So our students, as a part of my separations course, they have to make a dividing wall column design and work out how much more energy efficient is it than if you do a sequence of columns.
Well, it's good to see that there's at least the awareness is being created. I think if I look at what's being used in industry, it is still a lot of the traditional tools and we need to push more, I think.
What is very interesting, next week, you already referred to it, Harry. Next week, our session has 3 industrialists, and one of them is Robin Schulz. He has told on last September or last October, there was a dividing wall column seminar in Trondheim in Norway.
Yes.
He told the people who participated there that there are 5 companies in the world that have maybe 80-90% of all the dividing wall columns. It is a solution that is off the shelf available. If in the company the culture is we use dividing wall columns, then they go for it. And in a lot of other companies, they have not made the decision yet, and they don't do it.
Yeah,
There was a participant also from China showing pictures of what Igor Dejanovic called a bamboo forest of dividing wall columns. Literally tens of them on a row, really enormous parks with a lot of dividing wall columns. So there is quite some activity, I would say, worldwide. It's something that should grow further, I think.
In terms of the academic institutions, back to some of the things we talked about before we started here today, is in terms of funders, research funders, where they are putting their money. Because if distillation is not considered as being sufficiently of interest, then there isn't funding for it, and then the academics will not pursue that as a research area, and therefore they don't have the expertise that they need in order to teach the students at the level that is required for industry. So it becomes a vicious circle.
So that's a good task for the EFCE to also make it more aware to legislation and governments that there is actually something to be done.
Yes.
Okay, I think I would like to conclude the webinar today on time. That is not always possible. Again, I would like to thank the speakers. I would like to thank Martien Poe for organizing. And I would like to ask you to join next week, Tuesday, for our second distillation webinar. Thank you and goodbye.
Yes, thank you very much, Harry. And thank you very much for all the speakers today. And I hope to see you also next week. Bye-bye.
Okay, bye-bye.
Bye.